Hi students, as we are discussing the concept called as virtual memory from module number 4. From this chapter we have covered some of the topics, that is background, definition, benefits and how the virtual memory is going to be implemented. So there are two techniques we are using for implementation of the virtual memory. One is demand paging, another one is demand segmentation. So in this chapter we are going to cover or we are going to discuss or we are going to use the technique called as demand paging to implement the virtual memory. And this is a diagram that we have covered how the virtual memory looks, that is the larger than, we have seen the definition, virtual memory is the larger than the physical memory, and we are going to create a separation between the physical memory and the logical memory. This is called as virtual memory concept. And we have seen virtual address space, how it actually it will looks, and how the virtual memory is used for the implementation of the shared library concept. And then we have seen how the demand paging is used for the implementation of the virtual memory concept. Means if the bring a page into a memory only when it is needed here, otherwise that page is not going to be loaded. And we are going to use the concept called as valid and invalid bit to know which pages are in the memory and which pages are not in the memory. If, and this bit is associated with a frame number in the page table, and if the bit is set to 1 or if the bit is v, then the page is in the memory, or if the bit is 0 or if the bit is set to I, means it is not in the memory. During the address translation by the memory managed input unit, if the valid invalid bit in the page table entry is 0, then that page is not in the memory. If that page is not in the memory, we are going to raise the page fault. So this is one example that is going to show you how the page table when some pages are not in the memory. So this is a page fault we have studied. If the page is not in the memory, that is going to raise the page fault. Now the question is how to handle the page faults that we have covered here. So when you are going to load a M, you are executing instruction, and if this page is not in the memory, that bit is set to I, invalid. Now this CPU is going to trap to the operating system by raising the error called as page fault, and to handle that trap or the interrupt, operating system start working here. So it will locate which page is going or need to be loaded into the memory that is located in the backing store, and then that will be brings the page into a memory by identifying the free frame in the physical memory. Once it is loaded into the physical memory, it will be reset the page table here. Now the question is, if there is a free frame, we are going to load that page into the memory. Now what is the question here? If that page is or free frames are not available, what happens if there is a no free frame? Then we are going to apply the algorithms called as page replacement algorithms. So what is the use of page replacement algorithm? So we are going to find some pages in the memory but not really in use. Those pages are going to be shuck it out and stored into the backing store. So for this, we are going to use some different algorithms for the implementation of the page replacement. There are three different algorithms we are going to discuss. First in, first out, least recently used algorithm, and optimal page replacement algorithm. And the performance of the algorithm. So want an algorithm which will result in minimum number of page faults here. And when you are going to apply the page replacement, there may a same page may be brought into a memory several times. Before going to the implementation of these algorithm or discussion of the algorithms, we'll see the performance of the demand paging here. So as you know, what is the demand paging? If the page is required by the CPU for the execution, that is going to be searched. Means that page is demanded by the CPU for the execution. Then we are going to search the address translation unit, that is memory management unit. You will search in the physical memory. If that page is in the physical memory, then there is a no page fault. If it is not in the memory, then there is a missing, it will raise the page fault. So there are two values of the page fault, either 0 or 1. If the value of the p is equal to 0 means there is a no page faults. If the value of p is equal to 1 means every reference is a page fault. To calculate the performance of the demand paging, we are using the effective access time, EAT. The formula for this is 1 minus p into memory access plus page fault overhead plus swap page out, this is optional, and there is a no free frames, we are going to swap out the page. If there is a free frames, there is a no need of swap page out, and this time is optional here. If it is required, then only it will be swapped out. Swap page in, what is the time required here, then restart the overhead. This instruction which is aborted due to the page fault is going to be restarted after loading that missing page into the memory. So now take an example here by using the memory access time is equal to 1 microsecond. So now we are going to consider 50% of the time the page that is being replaced has been modified and therefore needs to be swapped out. So now consider here swap page time is equal to 10 milliseconds is equal to 10,000 microseconds, and the effective access time is equal to 1 minus p into 1 plus p of 15,000 into 1, sorry, E8 is equal to 1 minus p into 1 plus p 15,000. So there is a, we have considered swap of page time means there is a no page present in the memory, then there is a page fault. Now that will be considered as 1 plus 15,000 p in milliseconds. So why it is a 15,000? Because we are taking 50% of the time the page that is being replaced has been modified and therefore need to be swapped out. That's why 50% time is going to be added for the 10,000 millisecond. That is swap in time and swap out time. So after discussing the demand paging example, this is the time required we are going to calculate. So now we'll go to the next concept. Before going to discuss all the algorithms, we'll see the process creation. So virtual, another benefit that is going to be provided by the virtual memory allows the benefit during the process creation. There are two things we are going to use here: copy on write and the memory mapped files. These two topics we are going to cover in the next part of the video.